To probe the mysteries of cell division, a powerful laser beam is used to perform surgery on cells and chromosomes. Dr. Michael Burns of the University of California at Irvine has developed this remarkable technique of genetic engineering. A lens focuses the laser light into a tiny beam, which cuts through cells like a microscopic scalpel. The beam is so precise that it can be aimed at individual chromosomes and even used to snip off pieces containing a few genes. Dr. Burns finds 2 chromosomes and hits them with the laser. The cell is not destroyed. It continues to divide, but the chromosomes hit by the laser are expelled. Their messages will not be passed on to other cells. What comes next is another amazing feat of microsurgery, the manipulation of cells 1/1000th of an inch across. Carefully, all the cells around the one hit by the laser are scraped away. A nutrient fluid is added so that the single cell remaining can reproduce itself. Over the next few weeks, that single cell will divide into a colony of identical cells. Mysteriously, the destroyed chromosome is replaced by the remaining ones, thus restoring normal chromosome number to the cells. Other biologists have developed more precise techniques of genetic engineering. They can chop DNA molecules into pieces without destroying the molecule's ability to play the game of life. If they could link up these pieces in the right combination, they might solve the mysteries of the gene. If they could insert bits of DNA into living cells, they could create forms of life with new genetic structures. Their testing ground has been a tiny bacterium called E. coli. It lives in the human intestine, where its functions are largely unknown. The molecular biologists have found a way to splice genes from animals and plants into E. coli's well-known genetic structure. So cooperative are these bacteria that they willingly accept the foreign DNA and copy it as if it were their own. A revolution in medicine may be on the horizon. Already, gene splicing is being used to attack the human disease of diabetes. Scientists' long-time dream of genetic engineering is at hand. They are getting closer to the secrets of life. Since the discovery of DNA, biologists have been manipulating the very essence of life. Today, they can take DNA out of one cell and insert it into another. They can even mix the genes of different species. By transplanting animal genes into bacteria, they hope to find out how these genes work and are controlled. The process begins when a strain of bacteria is given an ample supply of food and gently shaken. In less than 24 hours, each bacterium can multiply 100 billion-fold. After the bacteria are harvested, a detergent bursts open their cell walls and sticky DNA strands spill out. Most of the DNA clumps together in a disorderly tangle. But nearby are tiny loops of DNA called plasmids. They are the key to the new technology of gene splicing. They will accept any genes the biologists can stitch into them. A fast-spinning centrifuge separates the plasmids from the rest of the DNA. Under ultraviolet light, a fluorescent dye makes the plasmid band visible. Carefully, the precious plasmids are removed. Now come the most crucial steps. In this simulation, a special enzyme is added to the plasmids. Like a pair of microscopic scissors, it snips open their DNA molecules at specific points. Other snipped genes can now be added to the open plasmid loops. The foreign DNA joins the plasmids, creating a new DNA molecule. The resulting loops, called recombinant DNA, combine animal genes with bacterial genes. They will be reinserted into other bacteria, giving those bacteria new genes. When the bacteria multiply, their new blueprint is copied over and over. Thus, science can make life forms with new combinations of genes. Dr. William Rudder is chairman of the biochemistry department at the University of California, San Francisco.
The possibilities for recombinant DNA technology are simply enormous. Not only are we going to revolutionize the understanding of the human genome and for genetics in general, but we will have profound effects on many aspects of biomedical science.
Over 40 million people are affected by the genetic disease called diabetes. In the United States alone, more than 1 million people inject insulin each day in order to stay alive. This insulin comes from the pancreas gland of animals. It is in short supply worldwide and often produces undesirable side effects.
My colleagues and I have been studying the expression of the insulin gene in the embryonic rat pancreas for several years. And one day I attended a faculty meeting in which Herbert Boyer and Howard Goodman were discussing their work on recombinant DNA. This excited me a great deal, and I cornered these two individuals after the meeting and said, "Herb and Howard, we just must clone the insulin gene."